In this video we'll be looking at exponential functions and logarithm functions, and I'd like to start off by thinking about functions of the form f of x equals a to the power of x, where a is representing real positive numbers. Now I'm going to split this up into three cases. First of all, the case when a equals 1. I'll then go on to look at the case when a is more than 1. And finally, I'll look at the case where a is between 0 and 1. So first of all, when a equals 1, this will give us the function f of x equals 1 to the power of x. And we can see that 1 to the power of anything is actually 1. So this is the linear function f of x equals 1. So that's quite straightforward. And secondly, I'd like to look at the case where a is more than 1. And to demonstrate what happens in this case, I'd like to consider a specific example. In this case, I'll choose a to be equal to 2, which gives us the function f of x equals 2 to the power of x. Now, a good place to start with these kind of functions is to look for some different values of the argument. So I'll start off by looking at f of 0, which is actually equal to 2 to the power 0, and we know that anything to the power 0 equals 1. Next we'll look at f of 1, which is 2 to the power of 1, and 2 to the power of 1 is 2. And we can look at f of 2, which is 2 squared, which is 4. So quite straightforward. And finally, f of 3, which is 2 to the power of 3, which actually gives us 8. I also want to consider some negative arguments as well. So if we look at f of minus 1, that gives us 2 to the power of minus 1. And remember, when we have a negative power, that means that we have to invert our number. So we actually end up with 1/2. If we look at f of minus 2, that gives us 2 to the power of minus 2. Once again, this negative power makes we've got 1 over 2 squared. And this 2 squared is 4, so actually gives us 1/4. And the final argument to consider is f of minus 3, which is 2 to the power of minus 3, which gives us 1 over 2 cubed, and 2 cubed is 8, so we get 1/8. I'm going to take these results now and put them into a table, and we can use that table to help us plot a graph of the function. So our table of values of x and f of x, and we just come from minus 3, minus 2, minus 1, 0, 1, 2, and 3. And the values we had were 1/8, 1/4, 1/2, 1, 2, 4, and 8. So we're going to plot these now so we can get a graph of the function. So do our f of x axis here, and our x-axis horizontally. So on the x-axis we need to go from minus 3 to plus 3. So minus 1, minus 2, minus 3, and 1, 2, and 3 this way. And on the vertical scale, the f of x axis, we need to go up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Make sure we label that. So now let's plot the points. Minus 3 and 1/8. Minus 2 and 1/4. Minus 1 and 1/2. 0 and 1. 1 and 2. 2 and 4, and finally 3 and 8. And so we need to try and draw a smooth curve through the points. And this is the graph of the function f of x equals 2 to the power of x. Now this actually quite clearly shows the general shape of graphs of the functions where f of x equals a to the x and a is more than 1. However, what happens when we vary the value of a? Well, by looking at a few sketches of a few different graphs, this should become clear. I have my axes again, f of x and x horizontally. We've just plotted the graph of this function, which went through 1 on the f of x axis, and this was f of x equals 2 to the power of x. If we were to look at this graph, this might represent f of x equals 5 to the power of x. And if I was to look at this graph, this might represent the graph of the function f of x equals 10 to the power of x. So what's actually happening here? Well, for bigger values of a, we can see that the output increases more quickly as the argument increases. Another couple of important points to notice here are, first of all, that every single graph that I've sketched here comes through this point 0, 1. And in fact, regardless of our value of a, f of 0 will equal 1 for every single value of a. Secondly, we notice that f of x is always more than 0. In other words, our output for this function is always positive. That's a very important feature of these kind of functions. The last case I would like to consider is the case where a is between 0 and 1. It's a case where a is between 0 and 1. To demonstrate this case, I would like to look at a specific example. In this case, I will choose a equals 1/2. So this means I'm looking at the function f of x equals 1/2 to the power of x. Now, as with the last example, a good place to start is by looking at some different values for the argument. So let's first of all consider f of 0. This will give us 1/2 to the power of 0. And as we said before, anything to the power of 0 is 1. Secondly, we look at f of 1, which is 1/2 to the power of 1, which is equal to 1/2. F of 2 equals 1/2 squared. So on the top, that just gives us 1 squared, which is 1. And on the bottom, 2 squared, which is 4. So we end up with 1/4. And f of 3 is equal to 1/2 cubed. So on the top, we get 1 cubed, which just gives us 1. And on the bottom, 2 cubed, which gives us 8. So we end up with 1/8. And as before, we also need to consider some negative arguments. So f of minus 1 gives us 1/2 to the power of minus 1. And remember, the minus sign on the power actually inverts our fraction. So we end up with 2 over 1 to the power of 1, which is just 2. F of minus 2 gives us 1/2 to the power of minus 2. which is 2 over 1 squared. You can see on the top we get 2 squared, which is 4, and on the bottom we just get 1, so that's actually equal to 4. And finally, f of minus 3 is 1/2 to the power of minus 3, which means we get 2 over 1, when we deal with the minus sign, cubed. So 2 cubed on the top, which is 8, and again, just a 1 on the bottom. So that just gives us 8. So once again, we're going to take these results and put them into a table so we can plot a graph of the function. So x and f of x again for our table. And we had values of the argument ranging from minus 3 all the way up to 3 again. And this time, the values were 8, 4, 2, 1, 1/2, 1/4, and 1/8. So let's plot this now on a graph. So vertically we get f of x, and on our horizontal axis we've got x. And we're going from minus 3 to 3 again. So minus 1, minus 2, minus 3, and 1, 2, and 3 here. And then we're going up to 8 on the vertical axis. 1, 2, 3, 4, 5, 6, 7, 8. So let's plot the points. First point is minus 3, 8, which is around about here. Minus 2 and 4, about here. Minus 1 and 2, about there. 0 and 1. 1, 1/2. 2, 1/4. And finally, 3 and 1/8. As with our previous example, we need to try and draw a smooth curve through the points. So and this represents the function f of x equals 1/2 to the power of x. And actually this demonstrates the general shape for functions of the form f of x equals a to the x when a is between 0 and 1. But what happens when we vary a within those boundaries? Well, sketching a few graphs of this function will help us to see. I'll just do some axes again. So we've got f of x and x. We've just seen this curve, which was f of x equals 1/2 to the power of x. We might have seen this, which would have represented f of x equals 1/5 to the power of x. Or we may even have seen something like this. Which would have represented maybe f of x equals 1/10 to the power of x. So we can see that for bigger values of a, so as we come down here, the output decreases more slowly as the argument increases. And a few important points to notice here. First of all, as with the previous example, f of 0 equals 1 regardless of the value of a. And in fact, as long as a is positive and real, this will always be the case. Second thing to notice, as with the previous example, is that our output, f of x, is always positive. So our output is always more than 0. So now we've looked at what happens for all the different values of a when a is positive and real. Now, one interesting thing you might have noticed is this. We've got some symmetry going on here. If I actually just put some axes down again here, so f of x and x, you'll remember that this curve here, passing through the point 1, was f of x equals 2 to the power of x. And also, this curve here was f of x equals 1/2 to the power of x. And we can see there's a link here, because one of these graphs is a reflection of the other in the f of x axis. And in fact, this could have been 1/5 to the x, and this could have been 5 to the x. Because generally speaking, f of x equal to ax is a reflection of f of x equals 1 over a to the x. And that is in the f of x axis. And 1 over a to the x can also be written as a to the minus x. So that's an interesting point to note. Now you might recall from chapter 2.3 that the exponential number e is approximately 2.718, which means it falls into the first category where a is more than 1, if we are going to consider the function f of x equals e to the x, which is the exponential function. So if I do some axes again, f of x vertically and x horizontally, then this graph here might represent f of x equals e to the x. And this is what the exponential function actually looks like. I might also like to consider the function f of x equals e to the minus x. And as we've just discovered, that is a reflection in the f of x axis. So this would be f of x equals e to the minus x. And remember this important point 1 on the f of x axis. So now we've looked at exponential functions, and we've looked at functions of the form a to the x. I'd now like to consider logarithm functions. Now logarithm functions take the form f of x equals the log of x to a particular base, in this case a. And as with the previous example, I'd like to split my analysis of this into 3 parts. First of all, looking at when a is 1. Second of all, looking at when a is more than 1. And finally, when a is a number between 0 and 1. And as with the previous example, a is only going to be positive real numbers. So first of all, what happens when a equals 1? Well, this means we'll get a function f of x equals the log of x to base 1. And remember, this is equivalent to saying that this number 1 to some power f of x is equal to x. Just like earlier on, this is equivalent generally to a to the power of f of x equals x. So when we look at this, we can see that we can only get solutions when we consider the argument x equals 1. And in fact, if we look at the argument x equals 1, there is an infinite number of answers, because 1 to any power will give us 1. So actually this is not a valid function, because we've got many outputs for just one single input. So that's for what happens for a equals 1. What would happen for a is more than 1? let's look at the case when a is more than 1. So this means we're looking at the function f of x equals, and in this case, I will choose a equals 2 again to demonstrate what's happening. So f of x equals the log of x to base 2. And remember, this is equivalent to saying 2 to the power of f of x equals x. So, as with all functions, when we get to this kind of situation, we want to start looking at some different values for the argument to help us plot a graph of the function. However, before we do that, we might just want to take a closer look at what's going on here. Because 2 to the power of f of x, in other words, 2 to some power, can never ever be negative or 0. This is a positive number, whatever we choose. And since that's more than 0, and that's equal to x, this means that x must be more than 0. And x represents our argument, which means I'm only going to look at positive arguments for this reason. So I start off by looking at f of 1. Now f of 1 gives us the log of 1 to base 2. Now what that actually means, remember, is that 2 to some power, f of 1, is equal to 1. So 2 to what power will give me 1? Well, it must be 2 to the power 0 give me 1, because anything to the power 0 gives me 1. So this f of 1 must be 0. So therefore, f of 1 equals 0. Next, I'll look at f of 2. And this means that we've got the log of 2 to base 2. And remember that this is equivalent to saying that 2 to some power, in this case f of 2, is equal to 2. So 2 to what power will give me 2? Well, we know that 2 to the power of 1 will give me 2. So this f of 2 must be equal to 1. And also going to look at f of 4. Now f of 4 means that we've got the log of 4 to base 2. And remember, this is equivalent to saying that we've got 2 to some power, in this case f of 4, is equal to 4. Now 2 to what power will give me 4? Well, it's actually going to be 2 squared, so it must be 2 to the power of 2 will give me 4. So therefore, we can see that f of 4 will actually give me 2. Now I also want to consider some fractional arguments here between 0 and 1. So if I look at, for example, f of 1/2, okay, this means we've got the log of 1/2 to the base 2. And this is equivalent to saying that 2 to some power, in this case f of 1/2, equals 1/2. Now this time it's a little bit more tricky to see actually what's going on here. But remember, we can write 1/2 as 2 to the power of -1. Because remember about that minus power that we talked about earlier on. So 2 to the power of something equals 2 to the power of -1. This something must be -1. So therefore, f of 1/2 actually equals -1. And the final argument I want to consider is f of 1/4. And this gives us the log of 1/4 to the base 2. So this is equivalent to saying that 2 to some power, in this case f of 1/4, is equal to 1/4. And once again, it's not an easy step just to see exactly what's going on here straight away. So we want to try and rewrite this right-hand side. Now 1/4 is the same as 1/2 squared, because 2 squared is just the same as 4. And remember about the minus sign, so we can put that onto the top, and we get 2 to the power of minus 2. So here, 2 to the power of something equals 2 to the power of minus 2. That something must be minus 2. So therefore, f of 1/4 equals minus 2. So what we're going to do now, we're going to put these results into a table so we can plot a graph of the function. So we've got x and f of x. And our x values we chose, we had 1/4, we had 1/2, 1, 2, and 4. And the corresponding outputs here were minus 2, minus 1, 0, 1, and 2. So let's look at plotting the graph of this function now. So, as before, we want some axes here. So, f of x vertically and x horizontally. Horizontally, we need to go from 1/4 to 4. So, we'll just go 1, 2, 3, 4. That includes everything we need. And vertically, we need to go from minus 2 to plus 2. So minus 1, minus 2, and 1, and 2. So let's plot the points. 1/4 and minus 2, first of all. 1/4 and minus 2. 1/2 and minus 1. So it's 1/2 minus 1. 1 and 0. 2 and 1. And finally, 4 and 2. So now we want to try and draw a smooth curve through the points so we can see the graph of the function. Excellent. So this is f of x equals the log of x to base 2. And actually this represents the general shape for functions of the form f of x equals the log of x to base a when a is more than 1. But what happens as we vary a? Well, let's have a look at a few sketches of some graphs of some different functions, and that should help us to see what's going on. So if I have f of x vertically and x horizontally, we've just seen f of x equals the log of x to base 2. And if I was to draw this, this might represent f of x equals the log of x to the base e. Remember e being the number 2.718, the exponential number. And actually this is called the natural log, and it's sometimes written ln x. And finally, it might have f of x equals log of x to base 5, maybe. So we can see that what's happening here, for bigger values of a, the output is increasing more slowly as the argument increases. Now, a few important points to notice here. The first one is to notice this point here, this 1 on the x-axis. Regardless of our value of a, f of 1 will always be 0. That's true for all values of a here. Second thing to notice is something we touched upon earlier on, is this point about the argument always being positive. And we can see this graphically here. We see we've got no points to the left of the f of x axis. And so x is always more than 0. The final case I want to look at is the case where a is between 0 and 1. And to demonstrate this case, I will look at the specific example where a equals a half. And if a equals a half, the function we're going to be looking at is f of x equals the log of x to the base 1/2. So remember, we can rewrite this. This is equivalent to saying that 1/2 to some power, in this case f of x, is equal to x. And as with the previous example, we need to think carefully about which argument we're going to consider now. Because 1/2 to any power will always give me a positive number. In other words, 1/2 to the f of x is always more than 0. And since this is equal to x, this means that x is more than 0. And so I'm only going to consider positive arguments. So first of all, I consider f of 1. F of 1 means that we've got the log of 1 to the base of 1/2. And remember, this is equivalent to saying 1/2 to some power, in this case f of 1, is equal to 1. So how does this work? 1/2 to some power equals 1. Remember, anything to the power of 0 equals 1. So f of 1 must be 0. Secondly, look at f of 2. This gives us the log of 2 to the base 1/2. And remember, this is equivalent to saying that we've got 1/2 to some power, in this case f of 2, is equal to 2. So how do we find out what this power's got to be? Well, we want to look at rewriting this number 2. And this is where the minus, the negative powers come in useful. So we can actually write this as 1/2 to the power of -1. If 1/2 to the power of f of 2 equals 1/2 to the power of -1, then these powers must be the same. So f of 2 equals -1. F of 2 equals -1. Now look at f of 4. Now f of 4 gives us the log of 4 to the base 1/2. And remember, this is equivalent to saying that 1/2 to some power, in this case f of 4, must be equal to 4. And once again, we need to think about rewriting this right-hand side to get a half so we can see what the power is. Now 4 we know we can write as 2 squared. And then using our negative powers, we can rewrite this as 1/2 to the -2. So if 1/2 to the power of f of 4 equals 1/2 to the power of -2, then these powers must be equal. So f of 4 equals -2. And also we want to consider some fractional arguments. So let's look at f of 1/2. F of 1/2 gives us the log of 1/2 to the base 1/2. So lots of halves. And this is equivalent to saying that we've got 1/2 to the power of f of a half, and that's going to be equal to 1/2. This, at first sight, might seem a little bit complicated, but it's not at all, because 1/2 to some power to give me 1/2, well, that's just a half to the power of 1. So this f of 1/2 is actually equal to 1. And finally, I'd like to consider f of 1/4, which is equal to the log of 1/4 to the base of a half. And remember, this is equivalent to writing 1/2 to some power, in this case f of a quarter, is equal to 1/4. And again, what we need to do is just think about rewriting the right-hand side. And actually, this is the same as 1 over 2 squared, which is the same as 1/2 squared. So 1/2 to some power equals 1/2 squared. The powers must be equal, so f of 1/4 must equal 2. F of 1/4 equals 2. So, as usual, put these results into a table so we can plot a graph of the function. Let's just do a table over here. X and f of x. Our arguments were 1/4, 1/2, 1, 2, and 4. And the corresponding outputs there were 2, 1, 0, -1, and -2. So let's plot these points. So first of all, some axes, f of x and x. So vertically we need to go from -2 to +2. So no problems, -1, -2, 1, and 2. And horizontally we need to go all the way up to 4. So 1, 2, 3, and 4. Let's plot the points. 1/4 and 2. 1/2 and 1. 1 and 0. 2, -1. And 4 and -2. As before, I'm going to try and draw a smooth curve through these points. Okay, excellent. And this is f of x equals the log of x to base 1/2. And actually this demonstrates the general shape for functions of the form f of x equals log of x to the base where a is equal to a number between 0 and 1. But what happens as a varies within those boundaries? Well, by looking at the sketch of a few functions like that, we should be able to see what's going on. So I'll just do my axes. F of x and x. And we've just seen f of x equals the log of x to base 1/2. Well, we might have had something that looked like this. And this might have been f of x equals the log of x to base 1 over e. And remember e, that exponential number. Or we might even have had something which looked like this. This might have been f of x equals the log of x base 1/5. So what's happening for different values of a? Well, we can see that for the bigger values of a, the output decreases more quickly as the argument increases. There's a couple of other important points to notice here as well. Firstly is this point 1 again on the x-axis. And in fact, we notice that f of 1 equals 0, regardless of our value of a. And that's true for any value. Secondly, is once again this thing about the positive arguments. We can see graphically once again that x has to be more than 0. So now we know what happens for all the different values of a when we're considering logarithm functions. Once again, you may have noticed some symmetry. This time, the symmetry was centred on the x-axis. If I actually draw two of the curves here, this one might have represented f of x equals the log of x to base 2. This one might represent f of x equals the log of x to the base 1/2. And don't forget, a very important point, 1. And we can see here that actually the base 2 function is a reflection in the x-axis of the function which has a base 1/2. And in fact, that could have been 5 and 1/5, or e and 1 over e as the base. Generally speaking, f of x equals the log of x to base a is a reflection of f of x equals log of x to base 1 over a, and that is in the x-axis. Excellent. So now we've looked at reflections in the x-axis, in the f of x-axis. We've looked at exponential functions, and we've looked at logarithm functions. The final thing I'd like to look at in this video is whether there is a link between these two functions. Firstly, the function f of x equals e to the x, remember the exponential function, and the second function, f of x equals the natural log of x, which we mentioned briefly earlier on. Now remember, this means the log of x to base e. Well, a good place to start would be to look at the graphs of the functions. So I'll do that now. We've got f of x and x. And remember, f of x equals e to the x. Run along like this, going through this important point 1 on the f of x axis. Because f of x equals e to the x. And f of x equals a natural log of x came from here and ran along something like this. Once again, going through that important point 1 on the x-axis. F of x equals a natural log of x. Now, is there a link? I think a helpful line to draw in here is this dotted line. This dotted line represents the graph of the linear function f of x equals x. And once we've put that in, we can see almost immediately that the exponential function is a reflection of the natural logarithm function in the line f of x equals x. What does that mean? Well, this is equivalent to saying that the axes have been swapped around. So to move from this function to this function, all my x values have gone to become f of x values. And all my f of x values have gone to become x values. In other words, the inputs and the outputs have been swapped around. So in summary, this means that the function f of x equals e to the x is the inverse of the function f of x equals the natural log of x.